unsupervised learning, which we started the week before last. And we are going to tackle one major algorithm known as the Kohonen self-organizing map, which is one of the major or most important type of clustering techniques. It has been discovered several decades back, I mean, almost 25 years ago, but people still use it nowadays, I mean, especially on bigger machines and on a bigger amount of data. So it's one of the major unsupervised learning. But there are almost 40 other unsupervised learning algorithms that people continue to utilize nowadays, especially with the advances on deep learning. And supervised based learning systems also have deep structure, as I'm going to comment later on this lecture. So what I am planning to do is to try to finish up with this lecture today, I mean, on unsupervised learning, in order for us to move to deep learning, hopefully starting later this lecture or as early as next Friday. I'm going to post assignment number 2 on Friday as per the schedule, and the assignment is going to contain material on support vector machine, on unsupervised learning, Kohonen self-organizing map, and also on an early part of deep learning system. So I will assign 1 or 2 problems on deep learning for assignment number 2. I will also email you this week about the schedule for our tutors or office hours starting next week, where 2 TAs will have office hour, one on Tuesday, the other one on Friday, and there will be one-to-one office hours where students could join during a team meeting, and I will send you the link and all the details. This is some of you guys, I mean, have requested to help you out with the material, and especially with some problems related to implementation. We have been relying on email and Piazza, which has served well so far, but I would like also to have you in touch with my TAs who are very proficient in the coding and implementation of this particular type of algorithm. So that we'll start. So one of the tutorials will be this Friday at 8 p.m. So we'll send you all the details later on today at 8 p.m. where Mahmoud is going to go with you over tutor material, and you can ask him some questions about the tutoring material. And starting next Tuesday, we will have 1 hour on Tuesday at 6 p.m. Because that's the time that where most of you are available, and the TAs are also available, and another hour at 8 p.m. on Friday. And you could meet with the TAs and you could ask them any type of question you may have on implementation aspects of the algorithm. So that's what I wanted to share with you at the start of this lecture. Before I start, I would like to mention as well that I will post the solutions of assignment 1 later today, alongside with some supporting material on unsupervised learning systems. So that's what I wanted to mention at the start of my lecture today. So unsupervised learning, we spoke about it the week before last, I mean on Friday, the week before, and we mentioned that it is another major component of machine learning systems. As you recall, machine learnings, I mean algorithms, machine learning algorithms have 3 major branches. One of them is supervised learning. We have seen so far support vector machine. We have connectionist model based on multi-layer perceptron systems. And we have another component or another branch of machine learning, namely the unsupervised learning, which I'm going to show you today, one of the major algorithms, the most transparent, if you would like to call it this way, and where you can get some insights about how the algorithm works. I find it to be powerful, and I found it to be also a scalable type of algorithm, namely the Kohonen self-organizing map. It was discovered 25 years ago by Professor Kohonen of Finland Institute of Technology in Finland. And The third one is the reinforcement learning, which we are not tackling in this course because one of my colleagues teaches that course during the summer, and the course is named 457C. Some of you may have taken that course, but even if you did not take that course, I will be happy to send to you some material for reading if some of you are interested in this area of reinforcement learning. So those are the three branches that machine learning is based on. And in one of the branches, which is supervised learning, we have one component which is deep learning system. So deep learning system is a subset of machine learning system, and we are going to start seeing that either starting later today or starting on Friday. And that is major components of machine learning algorithm today. And a lot of the techniques and a lot of the approaches that people are using nowadays are based on machine learning, based on deep learning systems. But I wanted to give you at least the ABCs of machine learning. We started with the perceptron, we went with the Adeline, the Madeline system, and then we went to the multi-layer perceptron, and then we saw another type of algorithm, namely support vector machine. And now we are going to the unsupervised learning component. Deep learning, as we are going to see, has two components, one supervised, the other one unsupervised. And I will share that with you when I talk about the structure and the architecture of deep learning systems. So let's look at this particular image here, and where we have, the system here, we have the input signals. So the input signals mostly are related to the features of the input of the system. So these are the attributes. As we have seen in assignment number 1, the attributes for problem number 4 are simply the features of the vector for each one of the elements that we have as input to the system. And those are called features, or they could also call attributes. So we have always the attributes of the system, and then through a particular structure, which we see it here as a gray with the output signal and the unsupervised based weight updating, the system is able to cluster the system into various type of components or clusters or categories. Okay, so this system through the unsupervised learning is going to be clustered. So cluster 1, cluster 2, and cluster 3 here, or cluster N, according to a certain mechanism that we are going to see in a few moments from now. So the system is not teaching the network or the structure, similar to what we have seen in the classifier of assignment 1 or the predictor of assignment 1, namely problem 3, where we have the inputs and then we taught the system what is expecting in part of the output, which is the mapping input to output. The same thing for problem number 4, where we have the features and then we have the classes. So that's those classes are supervised because we teach them. We teach the structure what to expect at the outset of the system. So here we are going to do differently. So we are going to extract these clusters, namely by having information about the input signal. And from the input signal, we are going to do certain type of operation about these type of attributes. And these type of operations are going to categorize or cluster these input signal, these type of data, into several type of clusters. So let's suppose that we have so many type of data input that we are inputting to the system. So each one of them is an exemplar or is a training type of data system. Each one of them has the dimension of the features. So here, this is the dimension of the features. So this is the inputs of the system. So it has feature with dimension D. So each one of the data that we are injecting to the system has as feature with the dimension D. So we have several of them, and simply we would like to cluster these ones. So this could be, for instance, cluster 1. This could be cluster 2. And these type of clusters, so cluster 1, cluster 2, are going to be categorized according to what is known as a weight updating mechanism that is going to do this clustering and which is going to improve it as we induce or we bring more type of data to the model. So that's in overall what we mean by clustering. So clustering, so we have a clustering one side and we have classification or prediction from the other side for supervised learning. So that's what I would like you to remember so far, from the supervised to the unsupervised. Okay, let's go to the next slide. So for the unsupervised type of algorithm, as I mentioned to you, there are almost 40 major unsupervised algorithms. So there are many type of algorithms. Many of them are powerful, but each one of them has its own characteristics. So researchers, they do a lot of work for developing these type of algorithms for a particular type of usage. Some of them are using them for computer vision. Some of them are using them for clustering anomalies in a particular product. Some of them are using them to cluster spam type of transactions from non-spam type of transactions. So ultimately, the system is able to do that. So there are several type of algorithms that are being utilized for several type of application. So we are going to focus in this unsupervised learning system on what is known as the Kohonen self-organizing network. So it is called Kohonen self-organizing network or Kohonen self-organizing map. So I have posted some material from my textbook, and I will also post some other material for reading for you on understanding even further on, for those of you who are interested in reading more, you can explore more details. But what I'm teaching you here in these slides is the more important components that I would like you to capture, and you can utilize it. And I'm going to illustrate it for you in one of the examples. So one major feature of this network is that the nodes distribute themselves across the input space to recognize groups of similar input vectors. So what does that mean here? So the system here, so let me share with you the structure of this particular network. So what the system tells us, so this is the feature map. So this is the input signals, x1, x2, x3, so it could be n features. So these are the input units. And each one of these units is connected to a whole network of nodes. As you can see, these nodes, they seemingly be connected, but in real world, they are not connected. But we are going to see later on that this connection is virtual. Ultimately, the system is going to cluster, elements of similar type of characteristics into cluster 1, elements of super characteristics into cluster 2. So this is how the system is going to work for this particular type of network. So these type of networks that have similar type of characteristics dictated by a certain measure of the features inputs are going to cluster automatically nodes that have similar type of characteristics. So these are going to be later on known as the clusters. But let me undo this type of things here in order for me to explain to you what we are doing. So this is the structure of the network. So it's composed of several type of nodes. And when the system is being trained, the system is going to be trained. So we are going to assign some random values of the weights here. And these weights here, so this is the weight components here. These weights are going to be updated as we progress in time. So these weights are going to be updated to, so this is weight 0, is going to be updated to weight 1. Similar to what we do to the perceptron and to the supervised type of algorithm in the multi-layer perceptron. So we go from one epoch to the next, to the next, to the next by updating this weight. So that after a whole set of epochs, the system now is going, when you provide it a certain type of input, is going to converge immediately to one particular cluster. So that's the idea of the Kohonen self-organizing map. So let me go back now to the earlier two slides. So we say that one major feature of this network is that the nodes of the structure that I just showed you distribute themselves across the input space to recognize groups of similar input vectors. So this is exactly similar to what I mentioned to you. So the network is going to have cluster of similar type of characteristics, accumulated together. It doesn't mean that one comes after the other. It doesn't make any, it's not meant to be that way. It could be one element from here and one element from here corresponding to one particular cluster. So in other words, the major feature of this network, nodes are going to distribute themselves across the input space to recognize groups of similar input vectors. So ultimately, when we have so this is the structure of the network. So this is the input vector, and of course it's connected with all the nodes of the network. Ultimately, we are going to have cluster of similar type of characteristics are going to be close to each other because of a certain type of metrics that we are going to choose. So these are going to compete among themselves to be close to each other in response to data that are in a certain type of metric close to each other. There is similarity between certain set of data that are going to make them belong to cluster 1, cluster 2, or cluster 3 of this particular network. So this is one of the major characteristics of this network. So it is a structure, it is a connection structure, because we have the input and we have an output, and in between we have the weights, basically, that we are going to connect between the input and the various type of cluster. So when we are going to inject a particular input, not all these type of nodes are going to respond. Only one particular node that has a certain type of privilege, we are going to see this particular type of privilege, is going to respond. So the vector of response is going to be very high. Here the vector of response is going to be low. Here the vector of response is going to be low. And this particular vector that has been with the largest type of module, with the largest type of strength, is going to be updated. All the other vectors are going to remain as such, and in other words, they are going to be weakened. If we don't strengthen them, they are going to be weakened. So we only update the nodes that have responded to a certain type of input type of data. Every time we are injecting an input of a nature similar to the one that has responded to this one, is going to strengthen this vector even further. So this is what is known as competitive learning. One single cluster is going to respond, the other one is not going to respond strongly, at least, and it's not going to have its weights going to be strengthened or to be updated. So this is known as competitive learning. This is a major components in the area of machine learning, where only output nodes that are responding to a certain type of input vector are going to be updated in terms of the weights. Because these vectors that we are seeing them are connected to these particular weights. Remember that this type of weights are connected to this cluster. So two input vectors with similar pattern characteristics excite two physically close layer nodes. So what we mean here, so again, let me draw this picture here. And again, let's have this input vector here, and it's connected to all the type of nodes. So let's suppose that you have node 1 here, you have node 2 here, you have node 3 here, you have node 4 here, and each node corresponds to a cluster, okay? So when we have one particular input that has responded, for instance, for this particular node, okay? So if it has responded strongly to that particular node, and we are going to see how the algorithm works there, then another similar type of input, so this is input 1, another similar type of input 2 that has certain type of similarity in terms of its feature is going to excite, again, this particular node. It's not going to touch these nodes here. Why? Because there are a lot of similarity between input 1 and input 2. So what we are saying, two input vectors with similar pattern characteristics excite two physically close layer nodes. Let me give you an example here, and then I will take one or two questions. So let's suppose that you have a bunch of fruits sitting on a sorting machine, okay, or sorting machine. So you have an apple, you have an orange, you have a pear, okay? The apple has, as you know, almost spherical shape, but it has a color which is red, let's say. The orange has also spherical shape, but it has a color that is orange. And then you have a pear which is completely different from the spherical shape, so it has an elongated type of shape. So let's suppose that you have a computer vision that is going to provide you characteristics, the color and the shape, let's say. Okay? So then we present a whole set of oranges, a whole set of apples, and a whole set of pears. And then the computer vision is going to look at one particular apple. So let's suppose that this is an apple that came, on the sorting machine, and the system is going to have a computer vision system, and it's going to provide two characteristics. So the apple is going to be spherical in shape, and the color is going to be red. So this is apple. So that's an apple. Let's say call it apple 1. Okay. And then another system comes. So the apple 1 here is going to excite a particular node. So let's suppose it is exciting this particular node here. And then we bring another, the sorting system brought us another apple, apple 2. So apple 2 is going also to provide us with spherical shape, with the redness similar to the redness of the apple 1. So the system now is going to be excited, and it's going to be responded through this particular node. So these particular weights, which have been updated when we injected apple 1, is going now to take apple 2, and knowing of the features of A1 and A2 that are very, very close to each other, is going to immediately assign this cluster of apple to this particular node. So this is what we mean here. Two input vectors with similar pattern characteristics, SR and SR, excite two physically closed layer nodes or similar nodes. Okay, so either very, very close nodes or even the similar nodes. We are going to see how we excite two physically closed layer nodes. So for now, let's simplify it, and they are exciting the same nodes. So in other words, the nodes of the Kohonen self-organizing network can recognize groups of similar inputs. So now let's go, and we have the computer vision system distinguished for us the orange 1. So orange 1 is going to be spherical in shape, but it's going to be orange color. So this one is going to excite another type of nodes, which might be close to this one because they have the same shape, spherical, but it has also the different type of color. So it's going to be a little bit farther away to this particular cluster. Okay, so next time when we are going to inject O2, orange 2, to the system, is going also to provide us something spherical and also orange color. And then the system also is going to bring here to the cluster indexed orange. Okay, so here what happens, we are going to consider this cluster apple and the cluster orange. They are two different clusters, but they are close to each other since they are in the upper layer of the network. Why they are close to each other? Because they have certain type of similarity. Look at the spherical shape. Look at the spherical shape. Moreover, red is not very far away from the color of the orange. So the more similar in features, the more closer the nodes are going to be. So this is what we call the topographic mapping. What does that mean, topographic mapping? The closer you are in terms of features, the closer you are going to be in terms of the nodes. So these nodes in the structure of the clusters are going to be close to each other. If we have this cluster, for instance, which responded to the apple, the red apple, and then we have another cluster which responded to the pear here, okay, which is green, which is elongated, as you can see, it is topologically far away from the apple because it has different characteristics, different features. And this is the essence of what is known as Kohonen self-organizing map. So here, we are not teaching the system at all. We are not telling it, this is an apple, this is a pear, this is whatever. So the system is going to deduce directly from the model that it has a certain type of characteristics, which is categorized by the distance between the features. So this is very important component that we need to understand. And this is what we mean by topographic mapping. So a topographic mapping means closeness of the nodes within the geometric structure of the network. So this is the geometric structure of the network. So you have a certain set of nodes, and the nodes that are close to each other are going to respond similarly to the same type of excitation. So we are not teaching the system with the teacher telling it this is an apple or an orange. No, through the pattern, the pattern characteristics, which are known as the features or the attributes, the system is going to cluster these particular objects. So this depends primarily on the pattern of the input vector, and it results in dimensionality reduction of the input space. I will discuss a little bit later on what we mean by dimensionality reduction of the input space. Okay, so this will be understood in few moments from now. Okay, so I would like you to understand what we mean by this particular topographic or sometimes topological mapping of the nodes. Okay. Okay, so let me take a few questions if you have any, so you can speak or you can also type. Do we have to feed in the feature? Okay, so let me read the first one. Do we have to feed in the features ourselves, or does the network figure out the feature on its own? This is a very good question. Actually, when you are developing a particular object, usually that particular object has a certain type of features. So in short, that particular apple or object, we are going to define it. So this is a certain type of system that has these type of features, it has this type of characteristics. So the system has a whole set of attributes. This is the first part. This being said, there is another more involved components of unsupervised learning, where the system is going to do what is known as feature selection. So the system is going to extract features that are the most relevant into the system. So for instance, here we have taken features that are most relevant. The color is very relevant for this type of fruits. The shape is very relevant, okay? The tactile, components, if we have a robot that is going to test the firmness of that particular fruit, is going to be very relevant. However, if we are going to see the size of these particular type of elements, let's say pears, apple or orange. Orange and apple have similar type of dimensions. So possibly dimensions might not be, in this particular case, a major feature to choose. But in this particular case, since we have a pear that has different type of geometry, the size is going to be also a component. So so at first, the easy answer is you select the features for a particular system. But for more advanced type of problems, the system is going to extract the most relevant features that are representative of that particular element of the data. I will mention that later when we finish up the part on the unsupervised learning, and I will discuss this a little bit more. But I will speak about it also later on when we are going to tackle deep learning system and why deep learning systems have proven to be very powerful approaches, very powerful techniques, because they are able to extract the best possible type of features for the system to input. So remember this aspect, and we will come back to it later on when I'm going to speak to deep learning. Second question, given this mapping ability, can we say Kohonen self-organizing network is a good generalizer? Usually when we are speaking about a generalizer, I mean, we would like the system to perform well beyond the training type of tasks. So I'm not going to say here compared with what a generalizer. There are several type of unsupervised type of learning system. So Kohonen self-organizing network, for now, let's put it this way, is a robust network as long as the features are well separated. Okay, so for now. So the system is able to do good generalization if your features are well separated, because we have the color and the dimension are completely different type of elements. So if we are going to input something of another, I mean, with different type of attributes, the system is going to be differentiating it and it's going to install it in another node. So in that regard, the system is a good generalizer. However, if we have an apple and if we have, I mean, apples of different size and apples of different colors, then we would like to have good generalization. How to do that? We are going to see it in the next few slides when we are going to talk not about one particular cluster with very, very strict type of characteristics, but we will talk about clusters that could accommodate different shapes, different colors of the apple. So if the system is able to do that in a robust way, and ultimately at the end of the day is going to separate the apples, whatever their dimension, whatever their color, from the oranges or from the pears, then we say that the Kohonen self-organizing network is a good generalizer. So depending on our parameters, similar to what we have seen in the course for the model, we are going to see these type of things. For the overfitting and the underfitting, the same thing occurs in unsupervised learning. Good question. Let's see here, what does it mean to excite a vector? So, okay, so now I'm going to go to this feature map, to this slide, and you will understand it a little bit more. So that answer is going to come in the next slide, which we have it here. So, and it's going to respond to you. So this is basically the input of the system. Okay, so this is the input to the system. So this, the characteristics, so the X1 means here the color, possibly, or the shape, which is spherical here. So this is the, I mean, how firm it is, the firmness of the object, and the color. So each one of them has a particular feature. So these are the attributes. And as you can see, these are completely different type of attributes. So they are far from each other. So they are very legitimate type of attributes. So if you go to a sorting, I mean, company, and they ask you to develop a self-organizing network and supervised type of network, you tell them, yeah, let's start with this early version of our network. So we have the shape, we have the color, we have the firmness, and these are major characteristics. Let's start with this, and then we are going to see more. Okay, so this particular system, we are going to excite them. So what does that mean, excite? So basically these type of element, each one of them has a particular value. X1 has a particular value, X2 has a particular value, X3 has a particular value. So they are like signals, okay? And these signals are going to be multiplied by these type of weights. Remember that this is weight 1 to node 1. So if we say that this is node 1, so weight 1 to node 1, it's weight 1. So weight 1 to node 2 is given by, let's say, weight 1, 2. So this is characteristic of the first feature to the second node. So we have a whole set of weights that are going to connect us between the input to the outputs of the system. Okay, so what we mean by excite, it means that we are activating these weights, but these weights are going to activate nodes more than others. So some of them are going to be activated by a small vector here, some of them by a little bit even smaller, some of them are going to be by a big vector here. Okay, so how come these particular vector is going to respond? We are going to see it in the next few slides. But for now, let's focus that our system here has made this particular nodes with the highest vector value. So let me go back here and undo that particular vector. So this is, the system has provided us this highest level of excitation. So the system has excited and it provided us with a certain type of vector value. So this excitation is no other than omega t times x, where the omega t is the transpose of the weights that connect us to this particular value, times x, the vector which has characteristics of x1, x2, and x3. Okay, so this is what is going to happen here. So this particular value here is going to provide us with this particular type of vector that is going to provide us with this particular connection. So when we look at it, so you are going to have three type of input, three type of weights that are going to come from each one of the input vector here. They are going to feed this particular one, and it's exciting it with this particular type of weight. So the system has provided us with this highest type of excitation vector. Okay, we are going to presume, because we are talking about the Kohonen self-organizing map, and we would like to make sure in our algorithm that all the nodes that are closer to this particular node should be also excited themselves. So these type of nodes should be excited, not in the same way as the central one, but in a way that is very responsive. So this one here should be excited, and this is the algorithm that we are going to check later on. So the algorithm is going to have one particular winner, because that's the competitive learning, but not only that, is going to make all the other components that are close to it also little winners. So this is a winner, the big winner, but these are also little winners. Why? Because the Kohonen self-organizing map works in the topological closeness. So if this is a pair here that has excited this particular node, then we are going to presume also a pair with a little bit greenish or a little bit dark green is going to excite this particular node here, this particular node here, this particular node here. So this cluster at the end of the day, after a whole set of training cycles, is going to start to respond only to the pairs. There will be other clusters that are going to respond to the apple. There are going to be other clusters that are going to respond to the orange. But for now, we are going to take the winner takes all, as we said, but also we are going to enhance the weights of these particular winners a little bit high, so that when they are excited in the future, they are going to be also part of the winning. So if you have big lottery here, winner tickets, so we have also those who are your neighbors are going to be a little bit winners as well, in order to avoid the jealousy between these type of this type of nodes and the other type of nodes. However, we are not going to improve the weights for these ones. So the weights for these ones remain random for now at the early stage of the training signal. They might become themselves winner for the apple. And then we are going to improve all their neighborhoods themselves according to the apple type of input. The same thing for the orange. We might have all these ones will respond to the orange. So this one might be a vector that is responding to the orange. So depending on how the system started, we are going to enhance those weights. So starting again from weights that are random in nature, we would like to enhance them and to give them certain type of patterns, certain type of shape, certain type of responsibility, so that in the future, when we are going to expose the same type of input unit to that model, the system is going to respond similarly. Okay, so that's the essence of the Kohonen self-organizing map or the Kohonen self-organizing network. So if we understand these components, then we can go to the next part for for developing the algorithm. Why I like to teach the Kohonen self-organizing map? Because it's visible. There are a lot of other algorithms in the fields of unsupervised type of learning, but they are not as visible and as transparent in understanding as this one. So this is what is known as topological or feature map. So it maps the feature here into a map of winners to respond to these particular type of systems. So when we said that we are going to reduce the dimension of the system for this particular model, it means that you have a whole set of input for the model. And then for this whole set of inputs, so we are going to have reduce the dimension of this system. So this one becomes C1 here. This becomes the C2 here. Okay, so these are the type of dimensionality reduction in terms of the input space. So the input space is going to be divided into cluster type of things. Okay, so this is what is known also as numerosity reduction. So basically, instead of representing so many type of data, so we say that we are going to represent these type of cluster as input to our system. So this is basically what I wanted to share with you at this particular stage in terms of the dimensionality reduction of the input space, okay? But I'm going to also talk about the dimensionality reduction of this feature space, which is going to be very, very important, and how we make it as a dimensionality reduction. So I will speak about it after I discuss about the algorithm. So before I go to the algorithm, I would like to ask if you have any question here. I will take very one or two brief questions if you have any. Otherwise, I'm going to go to the algorithm. So I hope that the excitement components of the question is understood. So that's what we mean by excite vector. So basically, it's going to activate a vector in the feature map. So this is the feature space. This is what we call the output space, if you would like to call it. And as you can see it, it's a 2D type of space. Okay, so let me continue on this since I started talking about 2D. So what is the dimension of this input space here? So this dimension is given by 3D. But it could also given by ND space. So it could have so many features for the system. But look now what we did. We went from 3D space of the feature space of the input vector to a 2D space. Why a 2D space? Because this particular element here that is going to represent the orange is going to be located in a 2D feature map. So it's going to be located at a certain geometric location within the feature map. So you went from 3D space to 2D space. So this is what is known as dimensionality reduction of the feature space system to the feature map. This is very important component in the fields of unsupervised learning. And this is basically what gives rise as well to the notion of feature extraction that a lot of people are utilizing to use it for several type of other algorithms. One of them included the deep learning systems. Okay, so when people tell you about dimensionality reduction from 3D to 4D to ND to 2D space, it means this particular type of dimensionality reduction for the feature space. Okay, so that's what I wanted to share with you here. Again, if you have any question, I will take it. Otherwise, I will go to the next page here. Okay, so the next page, this is the learning. So this is the learning mechanism of the system, and it's not very difficult. It's very easy, and there are a lot of algorithms out there that illustrate this particular example. And my TA Mahmoud will go with you as well on Friday to explain to you how he develops and how he writes a Kohonen self-organizing map. So the learning here permits the clustering of input data into smaller set of elements having similar characteristics. So you see here, so we have input data into smaller elements having similar characteristics. So these are the feature map. So the feature map is going to be mapped from the inputs data into the feature map. So from large input data into a feature type of map. So that's one characteristic. I just spoke about it in the last slide. It is based on the competitive learning techniques, also known as the winner take all. The winner take all is, this competitive type of learning that we discussed earlier. This is the winner take all. So if we go to the earlier slides, so when I said this is excited, So we are going to excite its little neighbors here, not match, but this is going to be the winner take all for the whole type of dotted rectangle here, as you can see. And this rectangle could also take other type of shape. So this what is known as the neighborhood. So this rectangle here is known as the neighborhood of the winner neighborhood. Okay, so we'll come to it in the next few slides. The neighborhood of the winner, which we are going to enrich it and which we are going to update it and adapt it to that particular set of improvement that we are going to allocate for this particular system. So winner take all. So this is the winner. No one here is going to be the winner. So once this one has declared itself winner, only this one and its little neighbors are going to be updated. None of these ones are going to be updated with this particular injection. So we inject an input, only one is going to be the winner, and its little neighbors are going also to be little winners. Okay, all the other ones are quote unquote losers for now, or they are, I mean, they watch how the other one is becoming fatter. This cluster is becoming responsive to a particular orange or the particular apple, and they look watching because they are not supposed to be winners for that particular type of excitation. So that's how the Kohonen self-organizing map works. Presume that the input pattern is given by the vector x. So let's suppose that we have here the vector x. So x has input x1, x2, x3. Of course, we can expand it to xn. Okay. Assume omega ig is the weight vector connecting the input elements to an output node with coordinated provided by index I and j. So here, this particular node here is going to be, located at this particular element. So this is a node which is given by n11. So it starts at this particular level of the 2D. So you can see that it is, this node 1 is excited by this particular weight, which is given by omega 1, 1. This node 1 is excited also given by omega 1, 1, 2, which is related to the first node and the second, this particular input. In other textbook and in this particular set of slides, so we reverse this notation. So this is known as omega 2, 1. So, let's put the standard. So this should be omega. So the one that connects this element here to this node is given by, so this one is given by omega 2, 1. So what it means that it's exciting, it is being excited by the second component of the vector x, and it is going to the first node 1. Okay, so that's how it is. So these are the connotation. Omega ij is the weight vector connecting the input elements by index I to the node element, which is given by j. Okay. NC is defined as the neighborhood of the winning output. So what is NC? NC is no other than this dotted line here. This dotted line here is the neighborhood. Okay, so in this particular case, it's given by this square or parallelogram. So this basically neighborhood is, or the diamond shape here. So it's given by the neighborhood. So the neighborhood has 1, 2, 3, 4, 5, 6, 7, 8 neighbors, and it is the winner, which is in the center. So that particular neighborhood, in this case, it's taken by a square. So in other type of neighborhood, it could be a diamond shape. In other type of neighborhood, it could be a diamond of circle. So basically, you can have a whole circle here denoted by, all the type of nodes that are surrounding this particular system. So when we say circle, so it's basically a multi-polygonal type of structure similar to this, because we are dealing with discrete type of representation of the system. So this type of neighborhood could take any type of shape, and it is defined according to a particular problem. So in image processing is different than in signal processing. In robotics or for navigating a particular system or a particular type of environment you can take different particular type of shape for these type of neighborhoods. So the neighborhoods are provided to you through experiments and through analysis for the system. So we have defined all these type of elements. So now NC is defined as the neighborhood around the winning output candidate. So NC here is how many? We have 1, 2, 3, 4, 5, 6, 7, 8 elements have to be updated. So when we update this one, all the other ones also have to be updated in a way that we are going to show in this particular case. So not only this one is going to take the biggest vector, this one also have to be updated to improve their weights. Why? In order for us to make sure that this is a topological mapping. Only the nodes and their immediate surrounding are responsive to a particular input. Okay? Okay, so its size. So this neighborhood, when we start training the system, its size decreases at every iteration of the algorithm until convergence occurs. So what it means here? So let's suppose that you have a particular type of winner here. And this winner has around it many type of neighbor nodes. So the nodes could be, more larger than the circle I described earlier. Okay, and then we can even expand it to here. So this is a second level of neighbor that the system was able to respond, especially when we have, sometimes thousands of original nodes that we wish to. Okay, so we'll take it. So it's a little bit awkward to draw on this particular shape. So this is the neighbor. So once this has responded, this particular element has responded, all the other one are going to be responding as well, and they are going to be updated. So this is what is known as the neighborhood here. So the neighborhood. So the neighborhood was large. And after we start the iteration, the system is going now to go even to smaller neighborhood to make sure that only the signal that are closest to the original element have been, taken care of or have been updated. So this is the original one at epoch 1. So this one becomes NC at epoch 2. Okay, and then if we have even more larger number of nodes, so we keep shrinking until we reach the central one, or it's very surrounding, elements that are closest to it. So this is what is known as the neighborhood updating. So we keep shrinking it as we go throughout the iteration. Okay. So now this is how the algorithm works, and this I would like you to spend a little bit of time to understand what we mean by this one. 1 second, please. Excuse me. So now we are going to go to step 1 for this particular algorithm. So we have defined every element here. So what we do, as we did with the multi-layer perceptron system, we initialize all the weights to small random values. So this is not strange. We have seen it in assignment number 1, and you were able to do it for number 3 and number 4. So there is no problem there. And we have seen that there are some tricks for number 3, where we should not have small, very small random values of the weights, because if they are very small, then they are going to be in the origin area of the sigmoid, and around the origin area of the sigmoid, it's going to provide us with certain type of shape that is linear, and we should avoid it. So those are tricks that you can only learn them through assignments or through real-world problem. You cannot see them in these particular notes, and that's why working on the assignment seriously is very helpful for you to understand what we mean by this particular type of elements. So we set a value for the initial learning rate alpha. So alpha, usually we take it between 0.1 to 0.9. So regardless, for in this particular example here, and this also, of course, it's going to be a parameter of the machine learning type of algorithm. And also we design our neighborhoods, NC. Okay, So the neighborhood NC is defined by all those nodes that are going to be in the perimeter of the winning nodes. And as we mentioned, the neighborhood could be square, it could be diamond shape, or it could be a polygonal shape with a certain symmetry around the center. So then what we do, we go to step 2 after we have provided this type of parameter. And then we choose an input pattern. So we choose the first pattern that comes to mind. So there is no way, I mean, the system automatically picks up one of the data sets elements that came to the system. And then what we are going to do the following. We are going to compare this particular element that we have chosen to what is known as the winning type unit. So this winning unit is characterized by the smallest distance between x and omega ij. Okay, so we pick one particular element and then we are going to compare that particular type of input with any type of weight that is located within the whole surface of the structure of the output of the system. So we compare that x vector with any type of omega j. Remember, what is the x? So the x is again determined by a characteristic. So this one, and this one. And of course, because we have omega 1 here, we have omega 2 here, we have omega 3 here. So then if we go here, so for omega, so let's say this is N8. So here we have the weight that is coming from the vector F1 is going to be given by omega 1,8. Okay, and then the weight provided by omega, the third element, is going to be omega 3,8. Okay, so we compare with these ones, we compare it with these ones, with these ones, with all the elements within this particular type of network. So we do cross section, so we scan for every node, and then we check which one has been similar to any of the weights, which is going to be random. So although they are random, but one of them is going to be the winner of the lottery because these elements x1, x2, and x3 provided certain type of strength. They are signals anyways. So because they are random, none of them is going to be the preferred other than the one that is going to be represent with the highest type of signal. So that one is going to be the winner. Okay, so we are going to select that particular, so let me go back to these things, and then we are going to select which omega ij has responded best to the input type of data x. Remember that x has been chosen randomly. The omega ij randomly, of course, among the whole set of data points. Remember that we have a whole set of data. So these, each one of them this could be representing apple, this could be an orange, this could be a pear. So this could be anything. So this could be an orange again. So we take one of them and we check which part of the network is going to represent to be the biggest. So the winner here is going to be the vector that was closest to the input vector x. So this is the third element, and which is very, very, important to understand. Now, once we have chosen this winner, around this winner, remember that there are some little winners. Remember the neighborhood. So we have a neighborhood. So we have the winner here, which has responded the highest, and we have here the little winners. So if this is a winner, its neighbors also are going to be also poor little winners. They don't have the biggest lottery ticket, but they are going to be winners because they are neighbors of this winner, which takes it all. So what we do, instead of, so remember that originally these type of weights were random values. We don't have any type of preference. They were random values. But now look what happens. From being random in the first step, they are now going to be taking certain type of structure. And that structure is going to be dictated by the input x and by this learning weight, this learning parameter alpha k. Okay, so what it says, the system, for all the words that have been a winner, if ij belonging to nck, which is this neighborhood, and including the winner, we are going to update it. If it doesn't belong to this neighborhood of the winners, then we keep it random. We keep it poor. We keep the strength of the weight as it is. We don't touch it. Okay? And alpha k is going to be an adaptive learning rate. This is similar to what we have seen in the adaptive learning for the multi-layer perceptron, where the adaptive learning rate for the learning, goes from smaller one, and then we improve it a little bit in order to improve the speed of the system as we grow in terms of the number of epochs. So this is going to be an adaptive rate, which is going to change according to a certain type of formula. I will share with you one particular formula in the next slides. NCK is the neighborhood of the unit C at iteration K. Remember, this is the C. This is the winning unit. And these are all the neighborhoods. Okay, so here we are reaching or adapting the weights that led to the best possible cluster or a representative of that cluster. And also we are going to enrich those that are going to be in its own neighborhood. So that's step number 4. So we continue with that. The learning rate and the neighborhood are decreased at every iteration according to an appropriate scheme. So here there are a number of different type of textbooks mean for the iteration. Some people look at the iteration is going from one input to the next. Input 1 to input 2. Then we do that, we call it iteration. Some other textbooks and some other algorithms, they go from I1, input 1, input 2, input 3, input n, which are all the data sets. After one epoch, the system is going to, update this particular type of weight. So it depends on what we are using. So in the example here that I'm using in this particular system, although this iteration, it means the iteration is in the form of epochs. So in the epoch, every epoch, the alpha k is going to be improved, every epoch of the system. And the neighborhood of the system is also going to shrink every epoch for the system. So the initial region is going to have a full size and then is going to shrink every time by a certain, so sometimes half size, sometimes quarter of size, depending on the statements of the problem. And then the learning scheme continues until enough number of iteration has been reached, or until each output reaches a threshold of sensitivity to a portion of the input space. So we continue. So we inject the first input. Then we improve the weights for the nodes that has responded to that input. And then we inject input 2. Now we have, at least in one cluster, some of the weights have improved and some of its neighbors have improved. We inject number input 2. Input 2 might go to another cluster, might go to another area of the feature map. We do the same thing. And then we inject input 3, and then we inject input n. We go through the whole set of input data. After a whole set of input data, we are almost assured that many of the weights have been at least improved once or several times if a certain number of inputs have responded to the same type of nodes. So imagine that our input 1 is an orange, which responded to cluster C1, C orange. And then our second one came to an apple. An apple is going to respond to another cluster with its neighbors, which are going to the winner. So also that new cluster, we are going to update it. We go then the peer, and then we improve it, and then we provide the winner cluster. So now we have at least improved several sets of weights related to these particular sets. And then since we have only 3 fruits, then another one is going to come to orange. Orange is going to go to the first cluster that responded to orange, and it's going to strengthen it even further. Why? In order for us to make sure that any time in the future, an orange is not confused with an apple. Because if an orange cluster has been strengthened to an orange input, then the noise is going to be very, very minimal. And going back to your classmate, your friends who asked about generalizer. So now if the system becomes very robust and has responded beautifully to all type of oranges that the system has seen. So in the future, when I bring an orange, its size might not be as big as the one that we have trained the system with. The system is going to generalize well. Instead of telling us this is an apple, it knows that even though its size is a little smaller, but the color, the firmness are related to orange. And the system, since it has been trained over many, many type of data points, is going to respond to an orange. And this way, we call the Kohonen self-organizing map is a good generalizer as long as you train it with various type of data that are close to each other and when the system becomes robust. So it depends on the parameters, it depends on the training type of data. Okay? So let's finish this set of slides with an example. So we go over it, slowly here, and to illustrate what we have. Okay? So we would like, so we have here 4 input data. So how many, what is the dimension of the input? It's 4. So we have x1 till x4. x2 and x3 here. Okay. So this is x1, this is x2, this is x4, this is x4. How many data points? We have 4 data points here, so the number is not large, but we have 4 data points. And these data points, they are not similar to each other, as you can see. But ultimately, we are going to request the system to cluster this particular type of data into 3 clusters. Look, we did not have anything here, but ultimately, because of these particular type of data points, the system is going to cluster them to 3 type of cluster. We don't know the first one is belonging to cluster 1 or this one also belongs to the cluster 1, but there will be ultimately 3 clusters that are going to respond to all these 4 type of data points. Okay, so here. Okay, so this is omega 1, 1 here. And this is omega 4, 1 here. And then we have also omega 1, so 2 here. And this is omega 1, 3. And then we continue with, going for each one of them. So we have a whole set of weights that are going to feed all these particular type of clusters. So once we have this particular data point, we are going to structure now. So this is the number of clusters that I'm going to test the system. So usually we provide the number of clusters. Sometimes we let the system cluster itself according to certain type of sensitivity. Some other times we assign the number of clusters for which we would like the system to cluster itself. So let's go here and let's say that we have, our original value at 0.3. So I did not mean to cross it. And then every time you go after one single set of epoch, in this particular case, we are going to multiply it by 0.2. So ultimately, we are going to take the number from 0.3 and make it smaller and smaller. So we start with the larger scope of all the nodes in the system, and then we make the system goes from 0.3 to possibly 0.001, depending on the number of iteration that the system is going to do. Okay, so possibly the system is going to stop at a certain level here, after the sensitivity of the system makes it, the weights become completely constant. Then we will stop. With only 3 clusters available and the weights of only 1 cluster are updated at each step, we are going to presume here, for the sake of making simple, NC is equal to 0. So, which means that here, if we have a number of nodes, then each node, which is going to be chosen as the winner, is going to be the selected winner for this particular system. So here we have how many? We said we have 3 nodes that are going to respond to the system. Okay, so this is our 3 nodes, and of course the input is going to be 4, similar to what we spoke. So the system doesn't have a neighborhood. Okay, to make it easier and to go faster for this particular example. So this is the feature map. So it is one single dimension, and it has a winning cluster here. And these are all the elements, as you can see, the weights here, all these particular type of elements. And when we have the winning, so the winning is going to be this one. We are not going to update these little ones. Okay, so let's start with the system. We are going to take, this is our matrix. As you can see, it's 4 by 3. 4 denotes the dimension of the inputs, and 3 denotes the dimension of the clusters. So the matrix is usually this in particular format. Initial radius NC, initial rate alpha 0 is equal to 0.3. So what we do? We inject the first, we excite the system with the first input vector. And then we do the step 3 to 5. So we compute the metric distance, 1 minus 0.2. So this is the Euclidean distance, which provide us with x minus omega c. Remember? So for each particular cluster, we have a measure, 1.39, 1.5, 171. Since we would like to minimize this distance, the first winner is going to be this one. Cluster 1 is going to be the first winner for this type of excitation. So the input vector is closest to output node 1. Thus node 1 is going to be the winner, and we are going to update it according to the formula that we have seen class. Okay, so this is omega odd minus x minus omega odd, which is given by this form here. Remember, this is a vector because we have x minus omega odd, which is the earlier one, which is this one. And this is give me 0.07. So what happens now? So now we have one node have responded well to the first vector, and the other 2 are not going to be updated. Agreed? Because we said only the winning node is going to be updated. Now let's inject pattern 2. Pattern 2 is going to respond to node 2. So we are going now to improve node 2, and we do the same thing as we did with node 1. So now we have this node 2 has been responsive to this particular type of injection of pattern 2. Let's go to pattern 3. Pattern 3 seems to be responsive to node 1. So the input vector is closest to output node 1. So remember that we see now that pattern 3 is closest to pattern 1 because of this L1. So we continue strengthening of this particular weight sets that have made response to node 1. So this is for pattern 3. Pattern 4 now is going to tackle the third node, which we haven't seen so far, and now we are going to update it as well. So node 3 now is going to be updated, and it's going to be given by this particular type of component. Okay, so this is how we are doing it. So this, we call it an epoch of training. And as you can see, this particular matrix has been updated twice at this level, and it has been updated once here and once here. So we are seeing certain type of shapes are taking place. So the first pattern and the third pattern have went to cluster 1. The second pattern went to cluster 2. So this is cluster 1, cluster 2, and the fourth pattern went to cluster 3. So we start seeing some shapes. So now we are going to redo the same thing from scratch, but now we are going to close and more focused type of learning mechanism for this particular system. So now we do it with 0.06 for this particular system. And then we continue until the system becomes clustered and until the weights here are not changing that much. After several type of epochs, these weights start to converge to a certain particular value, and they are only responsive to a certain type of cluster 1, cluster 2, and cluster 3. Okay, so this is what I wanted to share with you here about how we run the algorithm. The next 2 minutes, I would like to mention about the application. So there are a lot of applications of Kohonen self-organizing map, okay? And there are what is known as the neighborhood side. I mean, these are parameters that we can change. The shape, as I mentioned to you, circular, square, diamond, learning rate, decaying behavior, dimensionality of the neuron array. All of these have been variants of what I just showed you in this particular type of example. So let me respond to your friend here. Will we talk about PCA in this course? How does it compare to self-organizing map for dimensionality reduction? So PCA, because I mean we don't have a lot of time, I would like to start with the deep learning component. I'm going to speak about it when I'm going to tackle deep learning and about the feature selection. And if I have one lecture left after deep learning systems, before I start on the fuzzy system, I will give you one lecture on principal component analysis. Principal component analysis is an excellent type of unsupervised type of learning model, which is used for dimensionality reduction for the system, and it is used also for feature selection for particular sets of system for data sets where we would like to have dimensionality reduction of our particular model. Yes, we will speak about it, if not formally at the later part of the deep learning part, I will speak about it, I mean, next time when I'm tackling deep learning system. One last question before we go. Any question you might have? Always, I will be happy to respond to you by email or through Piazza if you would like. Okay, so I would like you to go through this particular part. I'm not going to go over Hopfield neural network, as I mentioned to you in the class, because we don't have a lot of time. I would like to spend more time on the deep learning and the later part of the course, which is related to fuzzy logic system. Okay, so these are some of the applications. I mean, every type of area, speech recognition, vector coding, texture segmentation, all of them have utilized unsupervised type of learning, and they are very, very useful in image processing, computer vision, and a wide range of application. Okay? Okay, so if you don't have any more questions, so I will end today's lecture, and feel free to email me, and I will be happy to help you. My TAs will be there also to support you if you have any question related to this particular material. I will post additional reading material for you, and to make sure that you have as much extensive exposure to this particular area as possible. Thank you very much for attending, and I'll talk to you soon. Okay, bye.